Okay, good morning, everyone. This is Practicum 12 from the Science and Technology lectures in physics, and I'm Hendradi Hadinata. I welcome you to join the Practicum today, which is about optics, in particular light propagation through transparent medium such as lenses. Right? In particular, we are going to focus on determining the focal length of positive lens, okay, which is converging lens, right? And the second test for today is that you can determine the focal length of the negative lens with the help of a positive lens, right? And in today's experiment, the equipment that you need are an optical table set, and for the software, you can use the usual Microsoft Word and Excel. Okay. I think the theory you already have in class during the lecture about optics, yeah, light propagation, in particular how light propagates through lenses. And as you can remember from the lecture, you can always imagine light as a ray, yeah, of a ray that is propagating in a straight line. And there are many applications of lenses. One of them is, of course, the microscope and telescope and the glasses that we wear, yeah, every day, which is a direct application of lenses, right? And as you may know from the lecture, there are basically two types of lenses, which are the positive or the converging lenses, or the diverging negative lenses, right? So in the converging lens, the light actually converge after it goes into the lens. Yeah. So if I can make an illustration here, the light after it propagates, yeah, through the lens, it will actually converge into one point, right? And this point here we call the focal point. And this is because of this Snell's law. Yeah, you know the Snell's law says the incoming angle is equal to n2 sinus the outgoing angle. And if we have a lens orientation like this, yeah, we can write the normal angle as the angle that is normal to the surface, right? This, right? So in this condition here, you have this law of refraction. And if you study the geometry of the lenses, you will find out that the refracting ray, yeah, will be in such a way as to converge in one point. The opposite is true for the other type of lenses, which is the negative lens or the global concave lens. In this case, the Snell's law will produce a normal that is going into the in this point, and as a result, yeah, if you study the geometry here, it will diverge. Okay, in the case that we learned today, the ray will converge into the focal point, right? So yeah, so as a consequence, you can calculate the formation of the image and also what happens if we have an object here. So for example, if we have an object that is located at some point here, yeah, it will follow the special ray formula, yeah, and as a result, we can calculate the distance of the image and so on. We can use this simple the simple laws that you already studied during the lecture, which is this formula here, yeah, where dO is the distance of the object from the lens and di is the distance of the image from the center of the lens, yeah. And remember, for the convergent or positive lens, yeah, The focal distance is positive, yeah. While for the divergent lens, the focal distance is negative, yeah. Keeping this in mind, yeah, you can determine the distance of the image using this formula below, yeah. Okay. So here you can see there are some conversion that you have to remember when doing the experiment. The focal length is always positive for a converging lens and negative for a diverging lens. This is the way that we can determine the distance correctly, and we can determine where the location of the image is, yeah. This is a convention in the sense that you have this red light, green light convention, where red light means you have to stop, and green light you've gone. If you follow the convention, you will get at the correct result. So we have to obey the shared conversion that we agree upon, right? If we agree on this, we have to be consistent so that we get the right results. If we don't follow the convention, we get something that is not in agreement, right? And therefore our calculation will be wrong, yeah. Here you can see do is positive if the object is left to the lens. So if your object is located yeah at the left of the length, yeah, the object, so in this case the O is positive. If the object is behind, so the light comes from this direction, if the object is behind the lens, then the O is negative, yeah. So in this sense, yeah, in the experiment you have to be careful where you put the object. Usually you put the object on the left, yeah, so the O is usually positive, yeah. So in the image, yeah, the image is positive if it's on the right, right? So it is the opposite of the O. So if the image that is formed is here, yeah, the image is formed is here. Here's the distance, the I. So the image is formed on the right, so it is a positive one, yeah. Where if it is on the left, it will be a negative one, yeah. Usually for lens, because the light goes through the lens, yeah, it can be either positive, of course, and negative, yeah. For example, as you have learned in class, there is a possibility the image form is a virtual image which is magnified. In this case, the I is negative because it's on the left, right? But if the image is here, it is then on the right. Yeah, here is on the left. So in this case, the I is negative. Here, the I is positive. Yeah. So these are the thing that you have to remember. And here you can use the special rays to determine the image, the final image. And as you see, if the image is formed by the direct arrows, you see the arrows here go pass through the image. This is called a real image because you can actually catch the image with a screen. If the image is virtual, you cannot catch the image. You can see the image with your eyes, which is a optical, yeah, like an optical illusion, right? But you cannot catch the image. You can just see the image. But the real image, you can catch it on a screen. You can display it on a screen. You can even put your hand on it, and the image will be formed at your hand. So in this case, because we have an invert image like this, yeah, we call it an invert image, and we call it a real image, not because it is inverted, yeah, because as I said before, it is formed by the direct rays that pass from object through the lens. Yeah. If we have instead of the lens a mirror here, then the image that is formed behind must be a virtual one, because the light will be reflected from the image, from the mirror. Yeah, if we have a mirror here, the image will be reflected, and as a result, the image that is formed behind the mirror is not a direct result of the arrow, but it's just an optical illusion, right? So it's a virtual image. is a virtual image because it is behind the screen. It's not formed by direct. The direct rays are reflected here. In this case, you have a lens, not a mirror. So the rays will pass directly through the lens and into the detector here. So we have a real image. Yeah. Okay, and the definition of DI and DO, here we have a positive DI and also a positive DO because it's on the left. This is on the right, right? So based on the convention that we just have here, DO is positive if the object is to the left and DI is positive if the object is to the right. So we have here both positive and negative. So both positive and positive, sorry. So for the DO plus DI here, we use both positive value for both of them. Yeah. So yeah, in this case, we don't have any problems, and also the focus is the focal is positive because it is a converging lens. Yeah, we have here a converging lens. So for the focus, this is also a positive value. Yeah, which makes sense because if these two are positive, this one is of course this will be positive, right? So we have this convention to have this agreement, so the results will be correct. Yeah. Okay. So consider the feature here. We assume the rays they go from the left to the right, which is usually the case, right? Uh, for the for such problems, you see, we assume the light coming from the left. Yeah, not always. Yeah. So what we are going to do is to place the object on the left of the lens and then capture the image. Yeah, that is formed to the right of the lens using the screen. Yeah. So for the experiment here, we use a real image because we want to display the image in the screen on the screen. Yeah. From the equation, if the image of the eye is positive, yeah, the image of the eye is positive if the O is larger than F. If the O is larger than 2F, then the image is minimized. Whereas for the O is in between the focal length and the 2F, yeah, the image is enlarged. Okay, this you can prove yourself actually when you do the experiment. Yeah. So how is the formation of a real image? Yeah, so you can follow here using the special rays, and you know that the rays that is parallel to this line here, yeah, the main line will be passed through the focal length. So this is the focal length, whereas here if the image goes into the point, yeah, in the middle of the lens, it will just go past. Yeah, it will just go past. So you have this kind of intersection between the two lines, the special ray, yes, and here in the intersection is defined as the image. Yeah, so the distance of the image is given here, which is positive. Again, this is also positive. Focal length is also positive, right? And this is how you do the drawings. Yeah. So what happens if you have here a converging lens? So a converging lens can be helpful to enlarge the object. So you have initially this kind of image here, which was initially DI. Now because of this second lens, this DI becomes a DO for the second lens, right? So you have 2 times calculation, and here you have no the DO. Yeah. Be careful with the side. Yeah. Yeah, because we have no a converging lens, and DO is on the right of the image. Yeah. So this in this case DO should be negative. Yeah. And here you have the new DI. Yeah. This is the new DI which enlarged the object. So think this of someone who has problems with seeing distance objects. Yeah, which is a person who has problems like me. Yeah, we need this minus or diverging lens, the minus lens, for adjusting the image so that the image will be behind formed in the retina of our eyes. Yeah, so the function of this to shift the image more behind the lens. Yeah. So for this problems with the eye sometimes, right? If we cannot see large objects clearly, the image that is formed is in front of retina. So using this lens, just like this one, the focus will shift now into the correct position here. Yeah. And we can see normally. Yeah, this is how our lens here, our glasses works actually. Yeah. And when you do this experiment, you can understand how the image will be formed. So the detector must be shifted a little bit more behind the lens so that you catch the bigger image. Yeah. And this is an interesting experiment to understand how our eyes work, how our glasses work. And okay, this is all what I want to say about the theory. Yeah. So for the practicum assignment, your assistant will be guiding you. Yeah. First, you have to determine the focal length of the converging lens, and to do that, yeah, you can use, of course, you can use this formula here. Yeah. You have the information about DO and DI, but you don't have information about the focal length. Yeah. Where is the focal length? So when you know DO and DI, you can, of course, determine the focal length. Okay. So you do this for the diverging lens, and I think there is a YouTube video, a video that you will see to do the experiment. Yeah. And the second experiment is such as like you put a negative lens or converging lens here, which will shift the image rather behind. Yeah. Okay, students, this is all from me. I hope you will enjoy the practicum. And if you have any question, you can ask the assistants. Uh, thank you for listening to me. I hope it is useful for you. Happy practicum and bye-bye. Thank you. See you next week.